Today what we are going to discuss is the time domain measurement of the lifetime of the fluorescence lifetime. And in the last day what we are discussing about three different methods for the time domain lifetime measurements. The first one is time correlated single photon counting method. In one word, this is known as TCSPC. And the other method which I am going to discuss maybe not today, maybe on the next class, is the fluorescence upconversion method. And I am not going to discuss this trick camera because probably time will not permit me to do so. Okay, so just let us compare this time correlated single photon counting setup and the fluorescence upconversion setup. Each setup has its own benefit and also each setup has some limitation of it. For example, this time correlated single photon counting method, the time resolution, right, or the IRF is not very high. Depending on system to system, this can go to 50 picosecond to 1500 picosecond or so. However, this fluorescence upconversion system, as you can see, this time resolution can go down to 0.2 to 0.4 picosecond. Right. So, in that sense, the fluorescence upconversion setup is superior to time correlated single photon counting setup. However, in the TCSPC setup, the advantage is that it has a very big time window, right. Time window is large, right. We can go to microsecond, no problem. But in this case, the time window is small. Typically, one go to 1 to 2 nanosecond time window for this. That means you cannot measure the fluorescence intensity for a longer time period in this case, although the time resolution is high. However, in this case time resolution is like a 50 picosecond, but we can measure for a longer time period, right. So, time window is very large. Okay, let us start the TCSPC setup, and as I said that for the time domain lifetime measurements, whether it is TCSPC or whether it is upconversion, what we usually do? We usually excite the sample with an ultra short light pulse, right. So, light is present for very short time and ideally the light is present so short time that this light pulse is treated as a delta pulse, right. So, delta pulse excitation. It means if I plot the intensity of excitation light as a function of time, then if this is the time axis, so the light will come like this way and then there is no light and this width is 0, right. So, this is my delta pulse. This is the ideal situation, but in reality it depends on the quality of the laser or the property of the laser, because I want to generate the light pulse as short as we can and that cannot be generated by normal light source, that what we have discussed like a filament bulb or the xenon lamp or deuterium lamp, those things we have already discussed. So, we need a special type of light source to generate such kind of short light pulse, right. What is that special type of equipment we need is a laser. So, special type of light source. So, we call this pulsed light source. And laser is very famous for that. We are going to discuss a little bit about this. So, once we excite this sample with this delta pulse light source as I have done here. So, in no time, so this is my 0, in no time the molecules will go to the excited state. On the other hand, if you use a broad light pulse for the excitation, what will happen? Just briefly I am drawing over here. Suppose you are exciting a delta pulse for the excitation. So, this is my 0 time. So, the population, so this is the excitation light pulse, and this is the excited state molecule population, excited state population of those molecules you are exciting. At 0 time, the population will be like this maximum, and then this population will decay. On the other hand, if you use such kind of light pulse, in this case this is not a delta pulse, right, has some width delta t. So, in this case this part of your light pulse will excite some molecule. So, the population is something like this. At time t equal to 0, here the intensity is maximum. So, I will get this maximum intensity. So, and at this time the intensity again small. So, I will get the intensity small. So, the excitation, right, the excited state population will take such kind of shape, and each of them will decay, and the decay will be distorted. That we are going to discuss later also. Okay, so, as you have understand that what I need a very short light pulse like this, short light pulse, and once you excite, you got this excited state population, whatever the population I have just normalized to 1, right, and then I will monitor how the population will decay, right, how the population will decay like this, and that is it. If I know this, then I will be able to calculate the fluorescence lifetime, because I know fluorescence lifetime, we already have seen that for fluorescence lifetime the dependence of this intensity I as a function of t is equal to I0, which is initial intensity, in this case is equal to 1 for this particular case, into e to the power minus t by tau, right. So, if I fit this measured fluorescence intensity as a function of time with such kind of equation, then simply I will get this value, because this t is my variable, t is over here t. So, I will get this tau, or I can say that when the population decay is about 63%, then I will get whatever the time, I can denote it as my tau, fluorescence lifetime. Okay. Let us go to this TCSPC setup, the setup by which we can determine this lifetime. As I said earlier, that if the lifetime is very long in the sense in hours, right, then each second you can measure the fluorescence intensity by your normal fluorimeter. So, no problem. However, the lifetime you know is in the order of nanosecond, that we have discussed. That means to let us say for such kind of nanosecond lifetime, if we start with intensity 1, then that intensity will going to be 0 in about 5 into tau, right. So, 5 nanosecond, right. So, that simply we can calculate over here for a lifetime of 1 nanosecond, right. So, my equation is I equal to I0 to the power minus t by tau. This tau is 1 nanosecond. Let us say I say that when I is equal to 0.001 times I0, then I said that intensity will completely decay, because this exponential function, it will be 0 at infinite time ideally mathematically, but for us when it is like just 1%, I said that the intensity is 0, right, finished. So, in this case what I can do ln 0.00, oh, so 1% I said, na. So, let me write 0.1. So, ln 0.1 is equal to minus t by tau, So, this will be equal to minus 4.6 equal to minus t by tau. So, t will be equal to 4.6 time of tau. That means, when the lifetime is about 1 nanosecond, the time window required to see the complete decay is about 4.6 nanosecond. And if this time window is 4.6 nanosecond, that is 0, and here is 4.6, here is 2.3, here is 1.15, like that. And if you want to see this complete intensity decay, right, you need to get several points over here, right, several points over here. That means, you need to measure the intensity of fluorescence, right, at every 0.1 nanosecond or 0.01 nanosecond or 0.001 nanosecond, something like that, which cannot be done, right, using your standard fluorimeter. It was okay if it is hour, but it is a nanosecond, right. So, I need to measure the fluorescence intensity at every picosecond or so, that means 10 to the power minus 12 second. That cannot be done so easily. So, what we should do? We should use some smart setup like this way. Just I will briefly explain you this setup. Here I use a laser over here, as you can see here. So, the property of the laser is such that it will generate the ultra short light pulse, right. So, this is capable to generate light pulse of short duration. Now, how short? That is the question mark, right. If the total time window, let us say for this 1 nanosecond, the total time window is 4.6 nanosecond, and if your light pulse is 10 nanosecond. So, obviously, we will not be able to see anything. It is simply like that. Using a meter scale, you cannot measure a millimeter. Like if your wristwatch does not have a second needle, right, you cannot measure 1 second or 2 seconds using your wristwatch, right. Very similar to that, if your excitation light pulse is much broader than this time window, right, then you will not be able to measure that. So, your excitation light pulse has to be shorter than this, right. So, for like a normal fluorescence lifetime measurement, right, if the lifetime is about a nanosecond, we usually use a light source of either 1 nanosecond or less than that. So, the light pulse should be about nanosecond, 1 nanosecond or less, right. Then I will be able to measure it, right. Okay. So, this light pulse, so these are the pulse light. So, pulse light means, please note that the light is present for some time, then for the rest of the time light is not present. Again light is present for some time, this width is the pulse width of the light, and then light is not present for some time. Again light is present, again light is not present, again light is present, then light is not present. That means, what I will going to get? I will get a series of such kind of pulses, and that series of pulses can be defined by its repetition rate, right. So, for example, if the time between these two successive pulse is T r, then and this pulse width is T p, right, then by defining these two quantity, by defining this T r and this T p, I will be able to characterize such kind of light. And another quantity you also have to define here, that is the wavelength of the light, because you need a particular wavelength for the excitation, and another property is the wavelength lambda. So, for a laser, what I say that I will fix Now, what is the color of the laser? Color of the laser. What is the pulse width? And what is the repetition rate of the laser? Repetition rate of the laser. Okay, so these three property I need to look at. Now, let us see that this laser is coming out of this laser, these pulses are coming out of this laser, and eventually it will excite your sample. Your sample is situated in the middle of the sample chamber, and then this fluorescence will come out of this, right, this then the fluorescence will come out of this. So, this fluorescence is not a single wavelength. So, you need to choose your lambda emission, your desired lambda emission, that will be done by this monochromator, and that will be directed to the PMT to measure its intensity, right. So, this setup works in a way that when this light, these short pulses are going to excite the sample over here, at the same time it will send one signal to a device called tach. This tach is time to amplitude converter. So, at the time this laser will going to excite your sample, at the same time the laser will send another signal to this device tach. The details of the tach I will discuss later, but for now let us take this tach as a kind of stopwatch. So, once it will send the signal to the tach, the start signal to the tach, it will start counting the time, right. And this stopwatch is a very nice stopwatch. It can count the time in the order of picosecond, right. So, this laser will send one signal to this tach, that means okay, now I have excited my sample. So, please start counting time. So, then this device will start counting the time. So, this obviously at that same time the sample has been excited. Now, once you excite the sample, several molecules will go from the ground state to the excited state. It depends on the how many photons are present in the each pulse and what is the concentration of your sample and so on. So, you will get a handsome population in the excited state, and as I said on the last day that this not all these excited state molecule will come back to the ground state at a particular time, but this is a random process. Some molecule will come back from the excited state to the ground state early time, some molecule will come back from the excited state to the ground state later time, some molecule will come back at the time t equal to tau, right. So, the molecule will come back from the excited state to the ground state, and I can measure this emission, right, by this PMT. The condition is that in this case that when one photon from this sample position will reach the PMT, when one photon from this sample position will reach the PMT, right, then this PMT will convert this photon to the electron and you will generate a electron pulse over here. So, you will generate a electron pulse over here, that is the current pulse over here, and that this current pulse will come and it will stop this stopwatch. So, now stopwatch will measure the time. So, what stopwatch will measure? Stopwatch will measure my tach. Here stopwatch means my tach. So, this stopwatch will measure the time delay between the start and the stop. That means, you have excited your sample and not immediately the photon is coming out of it. It may take some time and you will get a photon falling on the photocathode of this PMT, and this was converted to the electron, and then current pulse will stop it. So, the delay between excitation and emission plus the path length required to excite and then the whole process required to reach to this stop pulse, right. So, this is the difference between the start and the stop. So, in this case what you will going to get? You will get a time which is start or stop minus start, and for that particular time you will get a count, right. You will get a count. You remember that you have excited several molecules, right, in your sample chamber. Some of them will emit early time, some of them will emit at the later time, right. In this case, what I have to ensure that the first emitted photon is not necessarily be the first detected photon by this PMT. Let me explain it in a better way. Suppose this is my decay profile as I showed here. So, these are the probably the first emitted photon is at this time, short time. It is not guaranteed that these photon will come along this direction. It is possible that this photon will go in that direction, because this type of emission is a spontaneous emission, is a directionless. So, it can go to any direction, right. It can go to the upper side, lower side, left, right, and all these directions. Okay. So, when this particular time photon is along this line, then only it will be detected. Okay, let us consider that you got this particular time photon is emitted and it is along this particular line, in this particular line, and you got a signal that this count is for time t1, you got a count. Obviously, after that the photon of this one, photon at this time, photon at this time, photon at this time, photon at this time, all this time will be emitted until it will reach the 4.6 nanosecond in this particular case. But for this setup, we will not going to use all these emitted photon. So, once I will detect one photon which actually make the stopwatch stop, we finish the experiment and we will wait for the second excitation pulse to come and excite the sample. So, for one turn, one light pulse comes in, excite, the emitted photon is detected. Which emitted photon? I do not know. It could be this one, it could be this one, it could be this one, it could be that one. But in this particular case, I said that this is the emitted photon at time t equal to t1, and that photon has been detected. But these excited state molecules are much more, right. It is not only one, right. So, other molecule will also emit at the different times, but I will not going to consider those photon for this particular light pulse. What I will going to do? I will wait for all the excited state to come back to the ground state. So, I have to give enough time for relaxation, that means all the excited state molecule will come back to the ground state. Then when the situation is like before excitation, right. So, the situation is just like the before excitation, all the molecules are now in the ground state. So, now what I will do? I will use the next excitation pulse, let us say the next one like here. So, this will come and then again excite. So, again this light pulse will take all the molecules from the ground state to the excited state, and for in that cycle it is not necessarily that this photon will be directed along this path, it is not necessarily. It could be that this photon, this time this photon is directed along this path for the second cycle. So, this is for the second cycle, this photon probably directed along this path of the PMT, and let us say this is the time t4, right. So, for the first cycle I got a count at time t equal to t1. For the second cycle, I got a count at time t equal to t4, right. Then again I wait how long I should wait? I wait till all the excited state molecule will come back to the ground state. Then I use the third pulse, right, that means is my third cycle, right. This is the first, this is the second pulse, this is the third pulse, right, like that. So, when the third one will come, so that will going to be my third cycle. So, let us say for the third cycle, this photon which is emitted at very later time. So, this is my third cycle, this is T7, right, or maybe T17. Okay. So, this photon which is emitted at very late, that is the only photon which is directed to this path, Then in the third cycle, I will get a count at time t equal to T17, right. Now, consider you are repeating the same 10 million times. That means that same cycle, cycle 1, cycle 2, cycle 3, cycle n, cycle million times, cycle 10 million times, and so on. So, there is always a possibility that in that histogram you will get the photon of all these different times to be accumulated, right. So, that is what I was showing over here. So, here is the laser is sending one signal here to start the stopwatch, and then this is the pulse train, it is exciting, and then this photon is coming. It is not necessarily that the first emitted photon has to be first detected photon, because the spontaneous emission is directionless, and we do something over here to reduce the detection ability of the photon. So, most of the photon should be lost somewhere, right, that I am going to discuss later probably. So, that emitted photon, one of the emitted photon will reach the detector over here, and this detector will send the stop signal, as you can see here, and it will measure the time. So, as at different cycle, you will get a different point at different time, like, and this different at different time you will get a count. So, ultimately what you can do, you can plot a histogram like that, as is shown here. For the period 1, probably none of the photon has been detected. In period 2, one photon has been detected, here nothing, here one photon at this particular time, here one photon at this time, here nothing, here nothing, here nothing, here one photon at this time, here nothing, here one photon at this time. And if you sum it up, right, for 10 million times, then what you will get? You will get a such kind of histogram, which is nothing but the dependence of fluorescence intensity as a function of time, right. And now, if you fit this using your that equation, I equal to I0 to e to the power minus t by tau, then you will be able to get the fluorescence lifetime of your sample. Okay, so let me finish here, because time is up, and on the next day what I will going to show you that the basic setup which I have shown here will actually not going to work. We have to do several modification on this basic setup to actually get this time, because of several problem in this system, and those things we will going to discuss on the next class. Thank you.